Hi, everybody, and welcome to Bedtime Science, where the cosmos gets cozy and the apocalypse comes with a warm cup of tea. Tonight, you're staring up at the night sky. Maybe it's from a balcony, maybe through a dusty window, or maybe you're just imagining the stars from bed. Either way, you feel it, the sense that something is slipping away. Not quickly, not dramatically, but slowly, like sand leaking through a pinhole in time. The stars you see now? Some of them are already gone. Others, believe it or not, are speeding so far away from us that one day, their light will never reach Earth again. Like distant friends who stop calling. It's not them. It's the universe. And, of course, you probably won't survive long enough to say goodbye. So, before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. And hey, post your location and your local time in the comments. I love seeing where in the universe you're listening from. Now, dim the lights, maybe turn on a fan for that soft background hum, and let's ease into tonight's journey together. You lie still as space itself moves beneath you. Most people picture the universe like a room. Fixed walls, a ceiling overhead, maybe a slight draft from the past. But it isn't a room. It's more like a loaf of raisin bread rising in an oven. Except the raisins are galaxies, and the dough is space itself stretching, expanding, swallowing more and more of everything. When astronomers first noticed this, it was the early 20th century. A guy named Edwin Hubble, who sounds like he should be a cartoon raccoon but wasn't, measured the light from far-off galaxies. He noticed something weird. The light from those galaxies was redshifted, stretched out, longer wavelengths. Like the Doppler effect when an ambulance passes, but with galaxies instead of sirens. The farther away the galaxy, the redder the light. Which meant one thing. The universe was expanding. And if everything was moving away from everything else, then you could play the movie backward in your mind. The stars and galaxies squeeze closer together. The light blue shifted instead of red shifted, until finally, boom. A beginning. A single point. The Big Bang. But here's the cheeky part. That beginning didn't happen somewhere in space. It happened everywhere. Space wasn't just in the explosion. Space was the explosion. When the Big Bang happened, it wasn't like a firecracker in the dark. It was more like the dark itself turning into firecrackers everywhere, all at once. And ever since that first, impossibly hot moment, the universe has been growing. Not just the stuff inside it, but the stage itself. You lie in bed, and you imagine galaxies like tiny dots painted on a balloon. As the balloon inflates, the dots move apart. Not because they're moving, but because the surface between them is stretching. That's how the real universe works. And right now, that stretching is still happening. Quietly, relentlessly. Even as you listen, even as your lungs rise and fall. What's strange is that you can't feel it. The Earth isn't being torn apart. Your molecules aren't unzipping. That's because gravity and electromagnetism are holding your little patch of the universe together. But beyond the reach of galaxies, in the vast blackness between clusters, space is stretching. Just enough to make distant galaxies slip away a tiny bit more each second. You might be wondering, is there an edge to all this? A place where the universe stops? That's where it gets trippy. The universe doesn't have an edge. It's either infinite, like a video game map that wraps around, or it's curved in on itself like a four-dimensional sphere. Either way, if you start flying in a straight line and never stop, you'll never hit a wall. You'll just keep going and going until maybe, eventually, you loop back to where you started. Or not. Some physicists suggest that space is infinite, but expanding faster than you can ever cross it. Like trying to run up an escalator that keeps speeding up, always just ahead of your best effort. You blink at the ceiling. Time stretches with space. Light that left some galaxy 5 billion years ago might never reach us. Because the space between us and that galaxy is growing faster than the light can travel. Like trying to catch a bus that's driving away, on a road that's also growing longer behind it. Weirdly, it wasn't always this way. At first, the universe expanded rapidly, super fast, a period we call inflation. Then gravity slowed things down. Galaxies started forming, stars lit up, planets began spinning and complaining about Mondays. But lately, cosmically speaking, expansion has picked up again. As if something invisible and powerful is pushing it from behind. This is where the mood shifts. Because this invisible something? We call it dark energy. We don't know what it is. We barely know that it is. But it's there. And it's not going away. Some scientists call dark energy the most embarrassing discovery in physics. Like the universe handed us a mystery note that just says, figure this out, eventually. And we're standing there blinking, clutching our coffee, whispering, what? And so, you're left lying there, wondering, if space is growing now, will it keep growing? Will the stars we see vanish one by one, until we're left in a quiet, black void? hugging our little local galaxy cluster for warmth? Or will everything slow, crunch back in, and end in a reverse Big Bang, a big crunch? Or worse, will dark energy grow stronger until it rips apart galaxies, stars, planets, you? Historians still argue whether the universe is ultimately shaped by hope or entropy. But tonight, you breathe in slowly and accept that you live in a place that is changing in ways no eye can see. Expanding, shifting, whispering away into something colder, quieter, more distant. It's not a bad thing, necessarily. It's just the way things are. And, honestly, it's kind of poetic. You're part of a story that began with a single point, and now that point is billions of light years wide, humming with possibility. You close your eyes. The stars keep drifting. You fall back further now, into the past, deeper than dreams, into the moment when time itself was born. Imagine this. There is no before. Not because the records are lost, or the memories erased, but because before doesn't even make sense. Time itself doesn't exist yet. There's no ticking clock, no cosmic heartbeat. Just nothing. And then, everything. This is the Big Bang. Not an explosion in space, but an explosion of space. A point so dense, so hot, so absolutely everything that it contained all that ever would be. You can't stand beside it and watch. It's everywhere at once. You can't rewind past it, because time starts there. That's the frustrating magic of it. For a brief moment, less than a trillionth of a second, the universe undergoes something called inflation. Not the kind that ruins your wallet, but the kind that takes a microscopic speck of space-time and makes it bigger than a galaxy in a cosmic blink. It expands faster than the speed of light. Don't worry, Einstein's fine with that. Nothing in space breaks the limit. Space itself? Loophole. This was a time of chaos. Temperature? Insane. Particles? Not yet born. Light? Trapped. Time? Brand new and tripping over its own feet. And you, if you were somehow there, wouldn't be floating in fire. You'd be part of it. The stuff that would become you, your breakfast, your friends, your bones, was energy. Pure, rippling energy. Colliding, separating, bouncing through space that didn't exist a moment ago. Eventually, that energy cools, just enough to let the first particles form. Protons, neutrons, electrons, the holy trinity of stuff. This takes seconds, then minutes. The first hydrogen and helium nuclei assemble. Still no atoms yet. Electrons are too jittery to settle down. Historians still argue whether this early moment of particle formation locked in the fate of the entire cosmos. Did the exact balance of matter and antimatter, off by just a hair, doom the universe to expand forever? Or was it dark energy, waiting patiently in the wings, that would one day take control? Either way, the young universe is doing what babies do best, growing fast and glowing weird. Roughly 380,000 years pass, a nap by cosmic standards. The universe cools just enough for electrons to finally slow down and settle into orbits around atomic nuclei. Atoms. Real, calm, neutral atoms. The moment this happens, light is finally free to travel. The universe becomes transparent for the first time. And that light, we can still see it today. It's called the cosmic microwave background, or CMB. A faint glow, like the aftertaste of fire. It hums in every direction, invisible to your eyes, but detected by telescopes like ancient whispers from the beginning of time. It's warm fuzz from the universe's baby monitor. In fact, the very first satellite that captured the CMB in detail, COBE, in the early 90s, found the tiniest irregularities, temperature bumps that would later form galaxies, stars, and galaxy clusters. Tiny seeds of chaos, blooming into everything we see now. And now, a quirky little tidbit. In 1965, two radio astronomers named Penzias and Wilson accidentally discovered the CMB while trying to eliminate a weird hum from their telescope. They even cleaned bird poop out of the antenna, thinking that was the cause. Nope. Turns out it was the echo of the birth of time. Whoops. You lie there, imagining that first light still passing through you. It's stretched now, cooled, about 2.7 Kelvin, or just above absolute zero. But it's still there, in every room, every corner of space, softly saying, I was here. The universe keeps expanding, slowly. Galaxies begin to form. Clusters gather under gravity's patient hand. Stars ignite. Planets coalesce from dust and rock. And on at least one of those planets, you exist, warm-blooded, starborn, resting in the dark, thinking about all this. It's worth pausing here, because while the expansion is quiet now, compared to those early days, it never truly stopped. Like a balloon that keeps inflating, just a little at a time. But that little adds up. Light from distant galaxies gets stretched, again, that redshift. Not because the galaxies are zooming away through space, but because space itself is lengthening the ride. Some of those galaxies are so far that their light, even traveling for billions of years, still hasn't reached us, and may never. They're moving away faster than their light can travel in our direction. The universe has outpaced its own messages. It's a bit like someone trying to text you on a treadmill that's moving backwards. You never get the message, not because they didn't send it, but because the track is growing longer between you every second. And that's happening right now, while you rest, while you breathe, while you listen to the faint creak of the walls around you. The oldest light, the first time, the expanding birth. It's all still part of this moment. You close your eyes, letting that ancient heat wash over your thoughts. It's not fire anymore, just the faded warmth of a memory too old to forget. A cosmic fingerprint. And somewhere, in that vast beginning, was a hint, just a whisper, that this universe might not stop growing. You're still floating in the warmth of that first light, but now, the scenery is changing. What started as a soft hum becomes a soft pull. Galaxies begin to drift, not aimlessly, not chaotically, but in a way that feels strangely organized, like dancers in a vast, invisible current. You feel it, even now, though your feet are on the floor and your coffee mug hasn't floated away just yet. Here's where your brain might protest. Wait, aren't the galaxies flying away from us? Like in every science explainer ever? Well, yes, but not in the way you think. They're not little star-shaped rockets shooting off into the void. No, they're more like chocolate chips in a pan of rising brownie batter. The chips aren't moving through the batter. The batter itself is expanding, pushing everything apart. This is what cosmologists mean when they say, space itself is stretching. It's one of the most misunderstood ideas in modern science. And honestly, it feels wrong. Because we're used to things moving through space. Trains roll along tracks. Birds glide across the sky. But when space expands, it's not that objects are moving away from each other. It's that the fabric between them is growing longer. So here's the scene. You're on a galaxy, sitting quietly. Let's say your galaxy is the Milky Way, just for convenience. All around you, other galaxies seem to drift away. The farther they are, the faster they recede. A galaxy twice as far seems to move twice as fast. 10 times farther, 10 times the speed. But, and this is the trippy part, you don't feel it. There's no wind, no motion sickness, no cosmic Doppler nausea. Why? Because the space inside your galaxy isn't expanding. Gravity's grip is strong enough to hold it together. Like how super glue resists the tug of elastic. Your atoms, your planet, your solar system, all safe. The expansion only shows itself between vast, distant things. Galaxy clusters, superclusters, the dark lanes between the bright filaments of the cosmos. And remember, this isn't some slow, gentle push. This has been happening for over 13.8 billion years. Quiet, persistent, indifferent. Back in the 1920s, Edwin Hubble peered through his telescope and found this pattern. A redshift in the light from distant galaxies. A cosmic whisper that told him, something is expanding. And the farther away something is, the redder its light appears. This redshift isn't caused by galaxies moving like cars. It's caused by the light itself stretching, its wavelengths elongated as the space it travels through gets longer. It's like painting a stripe on a rubber band, then pulling both ends. The stripe doesn't move, the rubber does. And so, the light from ancient galaxies takes longer and longer to reach you. Some of it never will. Some galaxies are already gone from our observable universe. Still out there, maybe, but invisible forever. You'll never get their Christmas cards again. There's a quirky footnote here. There are galaxies that look like they're moving faster than the speed of light. And in a way, they are. But don't worry, Einstein's not rolling in his grave. That's allowed, because nothing's actually moving faster than light. It's just space itself expanding. Think of it as the carpet being pulled out, not the runner sprinting. Historians still argue whether early interpretations of redshift confused actual motion with spatial stretching. In the early days, people talked about galaxies rushing away. But now, we know the truth is subtler, more elegant, more haunting. You settle back deeper into the bedding of thought. Imagine this expansion continuing. More stretching, more silence, more distance between points of light. Your galaxy remains intact, but the ones around it? They dim. They fade. Some blink out entirely. Not because they've disappeared, but because their light can no longer reach us. There's a real consequence here, cosmic isolation. In the far future, tens of billions of years from now, new astronomers, should they exist, may look out and see nothing. Just blackness. No redshift, no galaxies, no evidence of a Big Bang. To them, the universe will look static, eternal, quiet. They'll wonder what we were talking about. Kind of rude, honestly. You can't help but smile. There's something both tragic and beautiful about that. Right now, we live in the golden age of visibility. The stars are still here. The galaxies haven't fully slipped away. The cosmic wallpaper is still richly patterned. You lie there, grateful that you live in a time when you can still see the universe breathing. There's one more weird detail. Because of the expansion, there's a limit to how far we can see the cosmic horizon. Beyond that, light hasn't had time to reach us. It might never. There's more universe out there, possibly infinite, but we're confined to this glowing bubble of visibility, about 93 billion light-years across, and getting bigger. And so, when you gaze up at the night sky, you're not just looking into space. You're looking into time, into expansion, into a fabric that's stretching under your pillow, through your ceiling, past the moon, between galaxies, into forever. The stars drift just a little farther away. You're getting used to this sensation now, that the sky is not still, not even close. Every pinprick of light you see is involved in a slow-motion escape act. But how do we know that? How can something as subtle as space stretching itself be measured, mapped, and trusted? The answer: redshift. Imagine light as a wave, like ripples on a pond, except this pond stretches from here to a galaxy 10 billion light-years away. When the galaxy emits light, say, from a star, it sends out a clean wave. But as that light travels through space, the pond gets bigger. The ripples stretch out. The light's wavelength increases. Now, here's the important part. Longer wavelengths equals redder light. So, when astronomers look through telescopes and see distant galaxies glowing redder than they should, they know something sneaky is going on. That red tint isn't just an aesthetic. It's evidence that the galaxy's light has been stretched by expanding space. This effect is known as cosmological redshift, and it's been one of our most loyal messengers from the distant past. It's how we realize the universe is expanding at all. It's like hearing an old recording and noticing the pitch has dropped, not because the voice changed, but because the tape itself was stretched. The more stretched the light, the faster the galaxy is receding. And the farther away the galaxy, the bigger the redshift. This is Hubble's law in action. Velocity equals distance times Hubble constant. Simple on paper, infuriating in practice. You might ask, what color would a galaxy look like to the naked eye if it were extremely redshifted? Answer: invisible. If the wavelength stretches far enough, the light moves right out of the visible spectrum and into infrared, then microwave, then radio. At extreme distances, galaxies vanish entirely, not because they blink out, but because their light has left the range your eyes can see. A cosmic vanishing act, one wave at a time. It gets weirder. Not all redshift is cosmic. There's also Doppler redshift, which happens when an object moves away from you through space. And there's gravitational redshift, which occurs when light climbs out of a massive gravity well, like a black hole's grip, losing energy, stretching its wavelength as it escapes. But cosmological redshift? That one's different. It's not caused by motion through space, but by the stretching of space itself. It's like mailing a letter, only to discover the road it's traveling on is getting longer while your mail truck is still en route. That's why your cosmic mail arrives redder and later than expected. Now here's a quirky tale for you. In 1927, a Belgian priest and physicist named Georges Lemaitre proposed the idea of an expanding universe based on general relativity. Einstein reportedly brushed him off. Later, when Hubble's observations confirmed redshift patterns consistent with expansion, Einstein famously called his earlier resistance his greatest blunder. Historians still argue whether Einstein really used those exact words, but the story endures. Redshift doesn't just confirm expansion. It also tells us the rate of expansion. That's where things get a bit awkward. Because when we try to measure this so-called Hubble constant, different methods give different answers. We look at ancient light, like the cosmic microwave background, and we get one value. We look at relatively nearby stars and supernovae, and we get another. And these numbers disagree more than they should. This is called the Hubble tension, and it's not just a nerdy quarrel. It might be the universe hinting that something fundamental is missing from our equations. Are we misreading the redshift? Underestimating dark energy? Is there new physics hiding in the static? No one knows. But the debate is getting louder. Back in your bed, under your quiet ceiling, you let this paradox hum in your ears. Somewhere, light is leaving a galaxy. That light stretches as space expands. It travels for billions of years. Eventually, it reaches a telescope. Scientists calculate how red the light has become, how far the galaxy must be, how fast it's receding. And then, they argue. Because every redshifted photon is both a gift and a riddle. It's like receiving a text message from someone you thought was gone, only to find the message delayed, distorted, stretched by forces neither of you understand. And here's the catch. Light is how we know anything. Everything we know about stars, galaxies, the edge of the universe, it all rides on these delicate waves of radiation. But those waves don't come unscathed. They carry distortion, history, clues wrapped in confusion. Every photon tells a story, but sometimes it mumbles. You lie still and picture it again. Galaxies blooming red in the far reaches of the universe. Their light, ancient and tired, crawling toward us across space that's growing beneath its feet. A redshift isn't just a measurement. It's a goodbye wave stretched across time. A reminder that the universe is in motion, even when it looks still, even when you're perfectly still. And that's the most poetic part of all. Right now, even now, everything you see in the sky is slightly older, slightly redder, slightly farther than it seems. You stretch out under the imagined dome of stars, but now you can feel something lurking behind the numbers and measurements. A presence, a mistake, or maybe a truth that came disguised as one. It came from Einstein. Let's go back to the early 1900s, when Albert Einstein was cooking up his shiny new equations for general relativity. The grand idea that gravity isn't a force, but the bending of space-time itself. These equations were bold, brilliant, and a bit too honest. Because when Einstein first solved them, he noticed something odd. The equations didn't describe a static universe. Left to its own devices, space-time should be doing something, expanding, or contracting, or swirling into chaos. But at the time, that didn't sit well. The universe, as far as anyone could tell in 1917, was eternal and unchanging. The idea that it might be growing or shrinking. Blasphemy to the scientific mind. So what did Einstein do? He cheated. He added a fudge factor to his equations, a term he called the cosmological constant, or lambda. This little mathematical patch acted like an anti-gravity force. It counteracted the pull of gravity and held the universe in a delicate, artificial balance. Not moving, not collapsing, just hovering. It was elegant. It was convenient. And it was wrong. Because a decade later, Edwin Hubble looked out into the night and saw redshifted galaxies fleeing from one another. The universe wasn't static. It was expanding. Einstein reportedly smacked his forehead and called the cosmological constant his biggest blunder. Again, historians still debate whether he actually said that, but it feels like something he'd say, doesn't it? The point is, he removed lambda, tossed it aside. The universe didn't need it. Except it kind of did. Fast forward to the late 1990s. Astronomers were measuring distant supernovae to figure out how fast the universe's expansion was slowing down. That's what they expected. Expansion was supposed to be dragging its feet by now, like a tired child at the end of a cosmic theme park visit. But that's not what they found. Instead, the supernovae were fainter than expected. That meant they were farther away than they should be. Which meant, and here comes the dramatic gasp, the universe's expansion was speeding up. What the heck? To explain this, scientists had to dust off Einstein's discarded cosmological constant and say, hey, sorry about earlier. We kind of need this back. And so, Einstein's mistake became a possible prophecy. The cosmological constant returned, not as a bug, but as a feature. And today, we use it to describe a mysterious force that's making the universe grow faster and faster. We call it dark energy. No one knows what dark energy is. It doesn't glow. It doesn't clump. It doesn't do interviews. But it's everywhere. Empty space seems to have energy of its own, a kind of quiet, passive push. And as the universe grows, so does the amount of empty space. Which means dark energy doesn't thin out like normal stuff. It stays strong. In fact, it dominates. Right now, scientists estimate that about 68% of the universe is dark energy. Only about 5% is the stuff you're made of, atoms, molecules, coffee. The rest is dark matter, but we'll whisper about that another time. So now you have this strange setup. Gravity is trying to pull things together. Matter clumps into galaxies, stars, and you. But dark energy is pushing everything apart, faster and faster. Imagine tug of war, except the other team gets stronger the more rope you let out. You can't win. Not long term. You lie there, eyes closed, imagining dark energy like a slow, invisible wind. You can't feel it. You can't measure it in your kitchen. But on a galactic scale, it's the loudest whisper in existence. And here's the kicker. Dark energy might be the cosmological constant, or it might not. Some scientists think it's a fixed number, just like Einstein guessed. Others believe it could change over time. Maybe it's growing stronger. Maybe it's an illusion. Maybe it's something else entirely, a new field, a trick of gravity, a property of vacuum itself. Theories are thrown around like stardust in a blender. Quintessence, phantom energy, scalar fields, modified gravity. Historians of the future will argue about which model, if any, was right. And what if we're wrong again? What if dark energy is just the latest fudge factor, the 21st century lambda, comforting us with math while hiding something more profound? That's the thing about the universe. It doesn't explain itself clearly. It prefers riddles. And sometimes, it lets you believe you've solved one, only to reveal it was a smaller piece of a much weirder puzzle. Tonight, that puzzle stretches above you and through you. Every breath you take is in a pocket of space-time that's getting bigger. Every second you count is shaped by a force we can't name. And every distant galaxy you imagine is on a journey you'll never see completed. Einstein may have blundered, or he may have glimpsed something none of us fully understand yet. Either way, the cosmological constant, his little bandage over a too honest truth, turned out to describe the fate of everything. You roll over, quietly impressed. Even mistakes in physics can shape the cosmos. You're starting to feel the scale of it now, not just how big the universe is, but how slippery. You think you understand a pattern, and then it slips sideways, like trying to measure a shadow on fog. And perhaps nowhere is that slipperiness more frustrating than in the fight over how fast the universe is actually expanding. It's called the Hubble constant. Sounds simple, right? Just a number that tells us how quickly galaxies are receding due to cosmic expansion. But oh no, it's a mess. A beautifully infuriating mess that's tearing modern cosmology apart at the seams. Let's break it down gently, like your fragile faith in definitive answers. Astronomers have two main ways to calculate the Hubble constant, denoted by the charming letter H. That's H naught, if you want to sound fancy. Method 1. You look at the nearby universe, relatively close galaxies, exploding stars, pulsating stars, and use them as standard candles. These are objects whose true brightness we know very well. So by measuring how bright they appear, you can figure out how far away they are. Combine that with how redshifted their light is, and boom, you get H. This method gives a value around 73 kilometers per second per megaparsec. Method 2. You look at the early universe, the cosmic microwave background. Yes, that warm baby blanket again. Using data from satellites like Planck, you analyze tiny fluctuations in temperature, plug them into a beautiful cosmic model, and after a bit of math you wouldn't wish on your worst professor, you also get a value for H. This method gives a value around 67 kilometers per second per megaparsec. The problem? Those numbers don't match. And the error bars, those little ranges of maybe, don't overlap anymore. This isn't just a rounding issue or a calibration error. This is a tension, and not the fun kind with dramatic music. It's more like two clocks disagreeing on what time it is, and they're both supposed to be perfect atomic clocks. Historians still argue whether this disagreement means we need new physics. Maybe our understanding of dark energy is flawed. Maybe time flowed differently in the early universe. Or maybe, just maybe, the cosmic yardsticks we're using are subtly warped. You shift under the covers, trying to imagine this in everyday terms. Say you're measuring how fast a cake is rising. One chef looks at the outer edge and says, it's rising at 73 millimeters per hour. Another chef peeks inside the oven at the dough's origin and swears it's only 67. And both chefs have PhDs and very stern eyebrows. This cosmic cake discrepancy isn't just academic. It matters, because H helps define the age of the universe, the distances between galaxies, and whether or not we're all doomed to float into eternal solitude faster than expected. If the higher value is correct, the universe is younger than we thought, by a few 100 million years. If the lower one holds, it's older. And remember, we're not talking about whether your birthday is off by a day. We're talking about whether the universe's birth certificate has been forged. There's another layer here too. Because some rogue teams, not rogue in the cape-wearing sense, but in the let's try something different sense, have used entirely new methods, gravitational lensing of quasars, or masers, cosmic laser-like radio signals, or even gravitational waves as rulers. These newer tools fall somewhere in between the two established values. It's like the universe is deliberately messing with us. And that brings us to the philosophical dread portion of our evening. What if the problem isn't the measurements, but us? What if we're missing something fundamental? Some property of the universe that subtly changes how light travels over billions of years? What if dark energy has evolved over time? Or what if the early universe had different laws of physics altogether? One quirky idea, called early dark energy, suggests there may have been a brief surge of repulsive energy shortly after the Big Bang, throwing off our calculations and bending the results like light near a black hole. It's speculative, yes, but speculation is sometimes all we've got when reality won't stop dodging questions. You breathe in, let it out slow. There's something beautiful about all this. We are, after all, a species trying to measure the shape and speed of everything, while standing on a spinning rock, using tools made from sand and fire. And yet, here we are, bickering over single-digit differences in the expansion rate of the cosmos. And those differences? They might hold the keys to secrets we can't even guess it yet. It wouldn't be the first time, either. Think of the 19th century, when astronomers were mapping Uranus's orbit and found it didn't quite fit Newton's laws. Instead of throwing out the laws, they proposed a hidden planet disturbing Uranus. Boom! Neptune was discovered. On the other hand, when Mercury's orbit was off, they tried the same trick and invented a phantom planet named Vulcan. Spoiler, it didn't exist. The answer was relativity. Same situation now. Either we're missing a planet, or a whole new theory of everything. You roll onto your back, imagining the scientists in their labs and observatories, hunched over spreadsheets, squinting at curves, hoping the numbers will whisper something new. And out beyond their windows, the galaxies stretch a little farther apart. Maybe the true value of H is hidden in a yet-to-be-discovered force, or a new particle, or a bold insight scribbled on a napkin during a midnight snack. Until then, we live with the tension. The expansion is real. That much we know. But how fast? And how forever? The stars don't say. They just keep drifting, each one a glowing breadcrumb along a trail we barely understand. And now, as you lie still beneath this web of expanding stars, something clicks into place. All this talk of speed, of galaxies flying apart, of space stretching, it leads you to the most obvious, most childlike question of all. Will it ever stop? It's a question that scientists have been asking since the moment they realized the universe was growing at all. It's the ultimate cosmic, are we there yet? The early thinking was straightforward, almost naive by today's standards. The universe is expanding, sure, but gravity exists, right? And gravity pulls things together. So, maybe, over time, gravity will win. It'll slow everything down, maybe even stop the expansion, maybe even reverse it. Like throwing a ball into the air, it rises, slows, stops, and falls back. The falling back part? That would be the big crunch, a kind of mirror image of the Big Bang. Everything, everywhere, all collapsing into one infinitely dense point. Dramatic, sure, but tidy. To understand if that would happen, you need to know just how much stuff is in the universe. Matter has mass, and mass means gravity. So the question becomes, is there enough mass in the universe to reverse expansion? This leads us to something cosmologists call the critical density. It's a specific value, a cosmic tipping point. If the actual density of matter and energy in the universe is greater than the critical density, then gravity eventually wins. If it's less, then expansion goes on forever. Simple enough. Except, we weren't sure how much stuff was out there. In the early days, when astronomers tried to tally up all the stars and gas they could see, they came up short. Way short. There wasn't nearly enough visible matter to reach critical density. So, some theorists crossed their fingers and hoped that maybe there was more invisible matter. Something hidden, silent, but heavy. This is where dark matter enters the scene. Another mysterious player. It doesn't glow. It doesn't emit radiation. It doesn't interact with light. But it has gravity, and lots of it. We only know it's there because galaxies spin faster than they should. Their outer stars don't fly off into the void. They cling tightly, as if held by a gravitational leash that shouldn't exist. Historians still argue whether Fritz Zwicky, the first guy to seriously propose dark matter in the 1930s, was dismissed too easily. He was eccentric, abrasive, and basically described his own colleagues as spherical bastards, because, he said, they were bastards no matter which way you looked at them. Colorful language aside, he was probably right about dark matter. But even after you include this invisible stuff, the total mass of the universe still doesn't quite make the cut. Gravity alone doesn't seem to be enough. And remember that plot twist from earlier? In the late 90s, when scientists looked at distant supernovae and realized that the expansion was actually accelerating, that changed everything. Because if the universe were slowing down, there was still a chance for a cosmic rebound. But acceleration means there's an invisible hand, not just preventing the collapse, but pushing everything apart faster and faster. Enter, once again, our spooky friend, dark energy. When you add dark energy into the equation, the balance tips drastically. Not only is there not enough matter to stop expansion, there's too much push for it to ever slow down at all. So back to your question, will it ever stop? Most scientists now think the answer is no. The universe will continue expanding, forever. But the flavor of that forever? That's still up for debate. If dark energy remains constant, like the cosmological constant Einstein proposed, then we get what's called a big chill or heat death scenario. Space keeps stretching, galaxies drift out of sight, stars burn out, black holes evaporate, and eventually, the universe becomes cold, dark, and lifeless. Just a vast, quiet nothingness with no events left to unfold. Cheerful, right? But if dark energy turns out to be dynamic, a field that changes over time, then we open the door to other endings. One possibility? The Big Rip. If dark energy grows stronger over time, its repulsive force could increase to the point that it overcomes all forces, not just gravity, but even the atomic bonds inside matter. First galaxies tear apart, then stars, then planets, then molecules, then atoms. The universe doesn't just stretch, it shreds. And everything ends in a cosmic scream of unraveling. Don't worry though, that would be tens of billions of years away. You have plenty of time to finish your tea. There's also the Big Freeze model, a more relaxed apocalypse. Expansion continues indefinitely. Galaxies move beyond one another's reach, and the universe slowly becomes a lonely, frigid desert. Stars die out. New ones don't form. And everything fades into a cold, eternal quiet. You pull your blanket tighter. In this model, black holes are the last players standing. But even they aren't immortal. Over unimaginable timescales, they emit Hawking radiation, slowly losing mass. A black hole the size of the sun would take about 10 years to fully evaporate. That's a number so big your brain will politely ignore it. Eventually, the universe becomes nothing but faint, fading radiation in an endless sea of expanding emptiness. You lie there, trying to picture it, not as a horror story, but as an ending. Quiet. Still. A final page that isn't violent, but slow and inevitable. Like the last embers of a fire dying under a soft breeze. The universe won't crash in on itself. It won't halt. It won't rewind. It will just go on, always, until it has nothing left to do. Now that you've wrapped your head around the idea of an ever-stretching cosmos, you might feel tempted to ask a deceptively simple question. What is the universe expanding into? And here's where your brain politely short-circuits. Because the answer, if you can even call it that, is nothing. Not nothing like empty space. Not a vacuum, or a blank stage waiting to be filled. Just not anything at all. The universe isn't expanding into something else. It's simply expanding. Period. There is no edge. No outer boundary. No shell we're ballooning inside of. The expansion of the universe means that distance between things increases, but not because we're moving outward into some larger room. It's the room itself that's growing. Every bit of it. Simultaneously. You're not flying through a tunnel. The tunnel is lengthening under you. This is where analogies get dangerous, but let's roll the dice. Picture an inflating balloon, not the air inside, but the surface of the balloon. Imagine it as two-dimensional for a moment. No thickness. Now paint tiny dots on the surface. As the balloon inflates, the dots move farther apart. Not because they're crawling away, but because the surface itself is stretching. Now, your three-dimensional universe is like that surface, except it's four-dimensional. Time adds another twist. You can't step outside of it, not even in imagination, because outside doesn't exist in a meaningful way. The balloon is all there is. If that makes you feel dizzy, you're not alone. Even Einstein once admitted that trying to picture curved spacetime in more than 3 dimensions made his head hurt. Historians still argue whether he said it with frustration or awe. And yet, that's what we're in. A self-contained, expanding, borderless reality. You lie there, staring at your ceiling, trying to grasp this. There's no outside, no boundary, just more and more space between things. And that space isn't empty, either. It's dynamic. It expands, it curves, it responds to matter and energy. It has texture. Even nothing in space is never truly nothing. Quantum mechanics tells us that empty space teems with virtual particles, blinking in and out of existence like cosmic static. Dark energy may very well be part of this vacuum energy. So the thing that's driving the universe to expand forever may be the same thing that ensures there's never truly nothing at all. Here's a weird twist. If you travel far enough in a certain direction, you don't hit a wall. You don't fall off the edge. You just loop around. At least, in some models. In certain cosmological scenarios, the universe could be finite but unbounded, like the surface of a sphere. It has a limited size, but no edge. If you kept traveling straight, you'd eventually end up back where you started. The universe as a sort of cosmic Pac-Man map. Other models suggest it's flat and infinite, stretching endlessly in all directions, like an endless piece of graph paper. In this case, expansion doesn't mean the universe gets bigger, but that everything within it spreads farther apart. Which one is it? The jury's still out. The current best data, thanks to the cosmic microwave background, suggests the universe is very nearly flat, like within a fraction of a percent, which implies it's probably infinite. But probably isn't satisfying when you're dealing with eternity. Here's a quirky fact. If the universe is infinite and matter is evenly distributed, as the cosmological principle suggests, then, somewhere out there, there should be exact duplicates of you. Not just one, but infinitely many. Because in an infinite space with infinite combinations, every arrangement must eventually repeat. Yes, somewhere, a version of you is lying in bed, hearing this exact sentence, but with slightly curlier hair and maybe a different brand of toothpaste. Now breathe through that for a second. This idea is called the infinite universe hypothesis, and while it's not universally accepted, it's weirdly unavoidable if certain assumptions hold. And the implications are wild. You don't just live in an expanding universe. You might live in a universe so big that every possible version of your life is being played out somewhere. It's like a cosmic multiverse, but without needing separate dimensions or branching timelines. Just one universe, one infinite stage, endless variations. You begin to understand why cosmology is as much philosophy as science. You're asking questions about reality itself, what it means to exist, to move, to be finite or infinite. And the answers aren't always clear. Sometimes, they're just questions dressed in fancier clothes. But here's what you can hold on to. Expansion isn't an explosion from a point into a void. It's every point moving away from every other point. It's the distance between galaxies growing. It's the light from ancient stars redshifting into whispers. It's the universe telling a story, not in words, but in distances. And you? You're made of atoms forged in stars billions of years ago. Atoms that remember how to stick together even as everything else moves apart. So as the universe expands into nothing, you stay here, anchored to your pillow, to your planet, to the moment. For now, the thought of the universe expanding into nothing may have left your brain quietly simmering, but you're still not done. Not even close. Because now that you know everything is stretching, galaxies drifting apart, light pulled thinner with each passing eon, you start to wonder, how do we even know what's out there? After all, we're sitting on a rock, orbiting a star, inside a galaxy. That's like trying to map the world while stuck in your backyard, using binoculars made of spaghetti. And yet, somehow, we've built a cosmic map. We've charted not only our surroundings, but the very shape and history of the universe itself. And we did it by listening to its oldest light. Meet the cosmic microwave background, or CMB for short. Think of it as the universe's baby photo, its very first, blurry selfie, taken when it was just 380,000 years old. A time when atoms first formed. When the universe went from an opaque plasma soup to something transparent. Before that moment, light couldn't travel freely. The whole cosmos was like the inside of a star, dense, hot, and glowing. Photons bounced off particles nonstop. But as the universe cooled, those particles settled into atoms, and light was finally free to roam. That light, the very first to break loose, has been traveling ever since. We see it today not as a blinding flash, but as a soft, cool microwave signal. It's all around you. Right now, in every direction, faint but persistent, like the whisper of the Big Bang itself. Here's a quirky bit. In 1964, two radio astronomers, Arno Penzias and Robert Wilson, accidentally discovered the CMB while trying to clean up noise from their radio antenna. They thought it was bird poop. Literally, they scrubbed the equipment. The signal remained. That noise was actually the afterglow of creation. Historians still argue whether they truly grasped the significance of what they'd found. But the universe knew, and so did the theorists who had predicted it years earlier. Today, we've mapped the CMB in exquisite detail. Satellites like COBE, WMAP, and Planck have given us full-sky images of this ancient light. It's not uniform. It has tiny temperature fluctuations, about 1 part in 100,000. Those tiny bumps, they're the seeds of everything. Galaxies, stars, planets, you. The ripples in the baby blanket of reality. And here's where it gets spicy. By studying the exact size, shape, and distribution of those bumps, we can infer the universe's composition, age, shape, and expansion rate. The CMB is like a crime scene photo, and cosmologists are the detectives, reconstructing the timeline with every pixel. From it, we've learned that the universe is 13.8 billion years old, that it's flat, or so close to flat that we can't tell the difference, that it's made of roughly 68% dark energy, 27% dark matter, and 5% ordinary matter, which is just a polite way of saying, we have no idea what most of the universe is actually made of. You breathe that in slowly. All the stars, gas, galaxies, and glorious nebulae, the things you can see with your eyes or telescopes, they're the rounding error. The leftovers, the decorative sprinkles on a cake, made almost entirely of mystery. But those mysteries still cast shadows. They bend light. They shape galaxies. They warp the CMB. In fact, one of the weirdest discoveries in the CMB map is a region called the cold spot, a large, unusually chilly area that defies easy explanation. Some say it's just a statistical fluke. Others whisper about a possible collision with another universe. Yes, you heard that right. A multiverse bruise. Do scientists take that idea seriously? Sort of. Carefully. With eyebrows raised and coffee mugs trembling. Another fringe theory suggests that cosmic inflation, the ultra-fast expansion of the universe right after the Big Bang, might have created bubbles of space-time, each one a separate universe with different physical laws. And maybe, just maybe, the cold spot is the scar where two bubbles once touched. You exhale, not because you understand it all, but because it's starting to feel deliciously impossible. And that's okay. The point is, we didn't just guess our way into understanding. We listened. We mapped. We modeled. We built machines that could read the faintest microwave whispers from the edge of time, and used those whispers to chart the entire past and future of space. And the CMB isn't the only clue. We also study large-scale structure, how galaxies and clusters of galaxies form vast cosmic webs. Filaments hundreds of millions of light-years long, with dark voids between them like the holes in Swiss cheese. These patterns match the tiny wiggles in the CMB. The blueprint became a building. So when you lie here tonight and stare into the dark, remember, that darkness isn't empty. It's packed with data. It's layered with history. And somewhere in that silence, photons from the dawn of time are still washing over you. Tiny messengers from a time before time. You are a creature of atoms shaped by those ripples. The same physics that painted the CMB also carved your bones. The same equations that explain galaxy clusters also describe the neurons firing as you imagine them. You are the universe thinking about itself, listening to its own echo, trying to understand its reflection in the microwave mirror. And even if the stars drift apart, even if everything ends in cold silence, that understanding, that curiosity, echoes louder than any redshifted scream. Let's go deeper now, not into space, but into time. You're drifting with the rhythm of this growing universe, and you've heard the whispers of its oldest light. But what if you wanted to rewind even farther? Not just to the cosmic microwave background, but to the moment before that, to the very first second of existence. Brace yourself, because the closer you get to the beginning, the stranger the story becomes. Rewind the cosmic film past galaxies, past stars, past atoms. You land in a moment known as the Big Bang. But here's the first plot twist. The Big Bang wasn't an explosion in space. It was an explosion of space. Every point in the universe sprang outward at once. There was no center. There was no edge. Everything was already everywhere. And it didn't begin big. It began small, infinitesimally so. A singularity, perhaps, or something beyond our physics. A point where density and temperature were infinite, where the laws of space-time break down. The earliest era, lasting just a trillionth of a trillionth of a trillionth of a second, is called the Planck epoch. We know almost nothing about it. Quantum mechanics and general relativity, our two best theories, simply don't get along at that scale. It's like trying to play chess underwater. Everything warps, glitches, refuses to cooperate. Historians still argue whether string theory, loop quantum gravity, or some other exotic model will one day unify the rules. For now, the Planck epoch remains a sealed vault. But a few ticks later, something astonishing happens. Inflation. Not the economic kind. This is cosmic inflation, and it's bananas. The universe expands at an absolutely ludicrous rate, faster than the speed of light. Space itself balloons outward, doubling in size again and again, all within a fraction of a second. This idea was proposed in the 1980s to solve a few puzzles that bugged cosmologists. Like, why does the universe look so smooth and uniform in every direction? Why does the CMB temperature barely vary across the sky, even though light couldn't have traveled between opposite ends that fast? Inflation fixes that by saying everything was once close together, sharing information, before suddenly exploding outward. It stretches quantum fluctuations, tiny blips in density, into cosmic seeds. Those seeds become galaxies, stars, you. And what caused inflation to start? What made it stop? We don't know. Maybe a quantum field called the inflaton did the job. Maybe it decayed into particles and radiation, reheating the universe in a process called reheating. Maybe it's part of a bigger, eternal inflation scenario where universes are constantly budding off, like cosmic champagne bubbles. Yes, there could be infinite universes, each with different physics. Ours might just be the one where life happened to bloom. You feel small again, but in a good way. After inflation, the universe is hot. Blazingly, unimaginably hot. Quarks and gluons zip around in a dense plasma, too energetic to form atoms. As things cool, particles begin to stick. Quarks combine into protons and neutrons. Those, in turn, will later form nuclei. But not yet. At about 3 minutes, nuclear fusion begins. The universe briefly acts like a giant star, fusing hydrogen into helium. This is called Big Bang nucleosynthesis, and it only lasts for about 20 minutes. After that, temperatures drop too low, and fusion stops. What you're left with is a universe made of about 75% hydrogen, 25% helium, and tiny traces of lithium. These elements are the building blocks for everything else, but it'll take billions of years before stars cook up heavier elements in their fiery bellies. But we're not there yet. The next major milestone doesn't arrive until 380,000 years after the Bang. That's when electrons finally calm down enough to bind with nuclei, forming atoms. This is the moment the universe becomes transparent, because light can finally travel freely. That's the cosmic microwave background we talked about earlier, the afterglow of this very moment. And then darkness. For hundreds of millions of years, there are no stars, no galaxies, just cooling gas. The cosmic dark ages. The universe is quiet, expanding, waiting. Eventually, gravity takes hold. Slightly denser regions pull in more matter. Those regions collapse. Stars ignite. Galaxies swirl to life. Light returns. You're living in a universe that took billions of years to assemble into complexity. It's not just the story of space. It's the story of time, woven from countless invisible moments. Here's a quirky twist. Some scientists think the Big Bang might not have been the beginning at all. Maybe it was just a bounce, a transition from a prior contracting universe to our current expanding one. In those models, the Big Bang is a doorway, not a genesis. Another idea? The Big Bang didn't happen once, but infinitely many times. Universes pop in and out of existence across a vast landscape of possibilities. Some die in a big crunch. Some rip apart. Ours. We got lucky. The beginning is a blurry place. But it's also your beginning. Every particle in your body was once packed into that hot, dense state. Every atom of oxygen you breathe, every cell in your body, every neuron now firing was born in this fire. And now, here you are, 13.8 billion years later, lying in bed, listening to the echoes of a moment so far behind the horizon that even light can barely remember it. You are not separate from the Big Bang. You are it, cooled and evolved, thinking about itself. The stars above you, distant cousins. The darkness between them, your ancestral womb. And the silence, just the universe catching its breath. You've made it through the fire, through the bang, the bounce, the blur. Now you're drifting forward in cosmic time, floating on that expanding raft of reality. But something keeps tugging at your mind, like a recurring dream you almost understand. If the universe is expanding, then, where's the center? Oh, the center. That old riddle. Here's the unsettling truth. There isn't one. There never was. When you imagine the universe expanding, your brain tries to make it like a balloon, one that inflates outward from a central dot. But remember what we whispered earlier. Space isn't expanding from a place. It's expanding everywhere. Every point in space is receding from every other point. There is no cosmic origin you can travel to. Wherever you are, you're at the center, because everywhere is the center. It's like baking raisin bread. As the dough rises, every raisin sees every other raisin moving away. No raisin is special. None is the start. The loaf itself is the expanding fabric of space. Of course, this makes the question even weirder. If there's no center, then what are we moving away from? And the answer, again, is not a location. We're moving away from a denser, earlier state of the universe. The Big Bang didn't happen in space. It happened to space. It's a hard truth to swallow. Your brain screams for edges, for centers, for symmetry. But the cosmos doesn't care what feels intuitive. Now, let's lean into another strange twist, the observable universe. You're not seeing the whole thing, not even close. Because light takes time to travel, we can only see as far as light has had time to reach us. About 46.5 billion light years in all directions. Yes, that's bigger than the universe's age in years. Space itself has been stretching during that time, remember? So the observable universe is a sphere centered on you. But here's the catch. It's also a sphere centered on everyone else. Every galaxy. Every distant speck of dust. This isn't an ego boost. You're not the cosmic VIP. It's just that everyone sees their own version of the observable universe, tailored to the speed of light and the age of space. Historians still argue whether this boundary, the edge of what we can see, is a hard physical limit or just a temporary horizon. Over time, more distant light might reach us. Or maybe not. Maybe, thanks to accelerated expansion, There are galaxies that are already receding faster than light can ever catch up. Yes, you heard that right. Because of expansion, some galaxies are already moving away from us faster than the speed of light. Not because they're speeding through space, but because space itself is stretching that fast. It's allowed. It doesn't break Einstein's rules, because no object is locally exceeding light speed. Space is just playing a bigger game. Those galaxies? We'll never see them again. Their light will never reach us. They've crossed a cosmic event horizon, like ships sailing past a fog so thick, their lights can never break through. The far future, if we wait long enough, will look empty. Other galaxies will fade from view. The night sky will go dark. Future civilizations might look up and see only their own stars. No hint of a grander structure. Without ancient records, they may never even know there was an expansion at all. You lie there, suddenly appreciating the time you were born into. A cosmic sweet spot. Not too early, when everything was opaque plasma. Not too late, when the stars have faded. But now, when the sky is alive with information. Another whisper enters your thoughts. Is the universe symmetrical? In a word, kind of. On the largest scales, yes, the cosmos seems isotropic and homogeneous. That means it looks the same in every direction and from every place. No special spots. No privileged perspectives. But zoom in, and the messiness returns. Galaxies form clusters. Clusters form filaments. Huge voids stretch between them. It's the cosmic web, a structure so vast and intricate it could almost pass for neural tissue. In fact, one fringe tidbit often cited, half jokingly, half wonderingly, is that the cosmic web and the human brain have similar large-scale patterns. Neurons connected by axons. Galaxies connected by gravity. Both operating with minimal information transfer over huge networks. Historians still debate whether this is coincidence, poetic metaphor, or some deeper truth, whether the universe is thinking, or whether we're just desperate to find ourselves in its shape. And yet, symmetry always invites curiosity. We crave balance. But the universe doesn't owe us that. It gives us hints of symmetry, sprinkled with chaos. Some theories propose a mirror universe, a counterpart to our own, where left and right are flipped, or time runs backward. Others dream of antimatter galaxies, made of particles that annihilate ours on contact. And then there's the idea of multiverse symmetry, a balancing act across parallel realities, each with its own parameters. Do we live in the only universe that works? Or are we just the lucky draw in a sea of trials? You pull the blanket tighter. The night feels bigger now, not just in space, but in possibilities. Because symmetry, or the lack of it, might decide how the universe ends. Whether it stretches forever, bounces back, or tears apart. Whether there's a matching timeline running in reverse. Whether your own existence is echoed across some hidden divide. And even if we never prove these ideas, even if they're just dreams wrapped in math, they push us forward. They ask better questions. They remind us that the story of the universe isn't just written in stars, but in what's missing between them. No center, no edge, no final word. Only more questions, floating outward. So far, you've drifted through inflation, bounced off the edges of space-time, which don't exist, and dipped a toe into a universe with no center and no edge. You felt the cold breath of dark energy and the awkward silence of cosmic loneliness. But now we come to something a little more personal. Let's talk about you. Because yes, while galaxies expand and stars die and photons from the Big Bang are still echoing around you like ancient lullabies, you're also made of that same stardust. That same hydrogen forged in the first minutes of time. You're not just in the universe. You are the universe, in motion. But here's the strange part. While the universe expands, you don't. You're not stretching like space. Neither is your house, or your street, or your planet, or your solar system, or even your galaxy. Weird, right? If everything is expanding, why aren't you 12 feet tall and floating through your kitchen like a runaway balloon animal? The answer is gravity, and electromagnetism, and all the other forces that keep matter bound together. See, expansion only works on the largest scales, where gravity is too weak to hold things together. That's why galaxies move away from each other, but stars inside galaxies don't. It's why the Andromeda Galaxy is approaching us, not receding. Local gravity overrides cosmic expansion. Even your atoms are unaffected. The strong nuclear force holding your protons together laughs in the face of dark energy. So the space between galaxies may stretch, but the space between your teeth? Safe. Unless you forget to floss. This separation of scales is a key idea. It keeps the universe from tearing itself apart on a Tuesday morning. It also means that expansion isn't some invisible wind blowing things apart. It's a property of space-time itself. Subtle, gentle, irresistible on large scales, but practically non-existent down here in the trenches. Now here's where things get a bit sci-fi. There are theories, fringe, but fun, that suggest we could harness expansion, that we could one day use the fabric of space-time itself as propulsion, not by pushing against something, but by manipulating space around us. This is the premise of the Alcubierre drive, a theoretical model where you shrink space in front of a spacecraft and expand it behind, creating a bubble that moves faster than light without violating relativity. Because inside the bubble, you're not moving. Spaces. Historians still debate whether this is genius or madness. Mathematically possible? Sure. Physically achievable? Probably not without negative energy, exotic matter, or a giant grant from NASA. But even if we never build warp drives, the idea still teaches us something. Expansion is neutral. It can't be turned off or on by choice. It's not a force in the usual sense. It's a global property, something baked into the structure of the universe itself. And that brings us to the question of, can we influence it? Can advanced civilizations, if they exist, manipulate expansion? The answer, so far, seems to be no. Not unless they can manipulate dark energy itself. And since we don't even know what it is, good luck with that. But there are speculative ideas. One of them is the Big Rip survival theory. If the universe is headed for a rip, some thinkers suggest that sufficiently advanced civilizations might be able to escape the tear, not by fighting it, but by jumping into pocket universes, seeding new regions of space before their own becomes uninhabitable. Others suggest island universes, places where intelligent beings create gravitationally bound oases, little sanctuaries that remain intact even as the rest of reality goes cold. Think domes of light in an ever-darkening cosmos. These are ideas on the edge of imagination. But so were black holes once. So was the Big Bang. So was the idea that Earth wasn't the center of everything. You shift under your blanket, wondering what civilizations, if any, have already faced these questions, who might be watching the same stars and wondering the same things, who might have already cracked the code of expansion and used it to their advantage. Maybe we're the first. Maybe we're hopelessly late. Maybe we're somewhere in the long middle. Either way, we're learning to ask better questions. And here's one that bites. If the universe is expanding, does that mean we're becoming more isolated? Short answer, yes. Every year, the most distant galaxies move farther from us. Eventually, some of them cross a point of no return, where their light will never reach us again. We lose contact, not because they moved away, but because space grew faster than light could compensate. It's like being in a conversation and suddenly, the signal is lost. Permanently. In the far future, billions of years from now, intelligent beings may find themselves trapped in tiny observable pockets, seeing only their local galaxy group. Everything else, gone, forgotten. Their cosmology would look nothing like ours. They might assume they're alone in the universe, not because they are, but because they've been cut off. It's not an apocalypse. It's worse. It's silence. And yet, in this expanding darkness, you are here. Now, breathing the stardust, thinking these thoughts. Floating, yes, but connected. For now, the universe is still generous with its light. Galaxies still beam their past toward us. Photons still cross the void, bringing stories from billions of years ago. We're still part of something vast, and we know it. You've made it halfway through this journey. The fabric of space may stretch forever. The galaxies may flee, but your moment in this story is real, measurable, precious. You're not expanding, but you are becoming, every second, a little more stitched into the cosmos. Let's take a breath now. You're still here, somehow tethered to your pillow while the fabric of reality stretches around you like a sleepy sigh. It's starting to feel familiar, this infinite drift. But just as your mind begins to soften into the rhythm of expansion, it's time we talk about a cosmic riddle that refuses to sit still. The Hubble tension. Sounds dramatic, right? Like a rock band or a bad breakup. But in truth, it's one of the biggest unsolved puzzles in cosmology, and it's giving scientists serious heartburn. First, a quick recap. The Hubble constant is the rate at which the universe is expanding right now. It's named after Edwin Hubble, the astronomer who first discovered that distant galaxies are moving away from us, and that the farther they are, the faster they go. This relationship between distance and velocity is called Hubble's law, and the number that defines the slope of that relationship is, you guessed it, the Hubble constant. Measure that number accurately, and you've essentially taken the universe's pulse. Easy enough, right? Well, no, not at all. Here's the problem. We get different answers depending on how we measure it. One method is to look at the early universe, specifically the cosmic microwave background. Remember that baby photo of the cosmos? By studying its fine structure with satellites like Planck and plugging those details into our best model of cosmology, called lambda-CDM, scientists can calculate what the Hubble constant should be today. That method gives a number around 67.4 kilometers per second per MPC. Now take a completely different approach. Observe the local universe, nearby stars, galaxies, and especially Type Ia supernovae, which are reliable standard candles. These exploding stars let us calculate distances and recession speeds with impressive accuracy. That method gives a number closer to 73.2 kilometers per second per MPC. See the issue? Those numbers aren't just slightly different. They're significantly different, well beyond the margin of error. We've measured both methods with stunning precision, and the gap remains. It's called the Hubble tension, and it's not just a quirk. It could be a sign that something's wrong with our understanding of the universe. Historians still argue whether this is just a statistical fluke, a measurement issue, or a sign of new physics hiding in plain sight. But the tension is real and growing. So what could be causing it? One possibility is that our standard model of cosmology, the lambda CDM model, is missing something. That little Greek letter lambda stands for dark energy, and CDM stands for cold dark matter. It's been the best fit model for decades, but maybe it's incomplete. Maybe dark energy isn't constant. Maybe it evolves over time. Or maybe there's a new, exotic particle involved, something that was around in the early universe but faded away, skewing the numbers. Scientists have proposed everything from early dark energy to new types of neutrinos to entire classes of physics that don't exist in current textbooks. Another idea? Maybe gravity behaves differently on cosmic scales. Some fringe theorists even suggest modifying Einstein's equations themselves, which is basically like rewriting the laws of reality with a pencil and hoping the paper doesn't catch fire. Here's a quirky tidbit. Back in the early 20th century, Hubble himself measured a value of the constant that was wildly off, around 500. His tools were primitive, and his assumptions flawed, but it still shows how tricky this measurement can be. We've been chasing the true expansion rate for nearly a century, and the trail just got weirder. Still, science thrives on tension. This is how progress happens. When numbers don't add up, when theories start to groan under the weight of evidence, that's when breakthroughs sneak in. Maybe one day the Hubble tension will resolve. Maybe it'll lead to a revolution. Maybe it'll do both. For now, we live in an awkward in-between. Two measurements, one universe, and a stubborn gap that refuses to close. You lie there, imagining cosmologists pacing in their offices, rubbing their temples, whispering to whiteboards. Not in defeat, but in fascination. Because this isn't failure, it's the thrill of not knowing. The kind of tension that means discovery is close. And if you're wondering why it matters, why this weird numerical mismatch keeps scientists up at night, remember this. The expansion rate sets the stage for everything. It tells us how big the universe is, how old it is, what it's made of, where it's heading. Change the Hubble constant, and you tilt the timeline of reality itself. It's like measuring your heartbeat and finding two wildly different numbers, depending on whether you check your wrist or your neck. One of them is off, or both. And the only way to know for sure is to listen harder. That's what science is, listening to a noisy, crackling universe and trying to hear the pattern. You turn onto your side now. The night outside is quiet, but your mind is buzzing with cosmic static. The gap between 67 and 73 becomes a gap between worlds, between what is, what was, and what might still be revealed. The universe expands. The numbers don't agree. And in that disagreement, truth waits, smirking behind a veil of stars. As the silence deepens and your mind softens around the paradoxes of expansion, you begin to feel it. Not just the enormity of space, but the shape of time itself. Because the question that lingers now, floating gently just above your pillow, is the one none of us can quite escape. How will it all end? You've heard echoes of this already. The expanding space, the galaxies slipping beyond our grasp, the eerie silence waiting at the edges of the future. But now, we wade into it fully. Let's talk about the possible fates of the universe. Option 1. The Big Freeze, also known as heat death. This is the scenario that most physicists consider likely. In this future, the universe keeps expanding forever. Galaxies drift further apart. Stars burn out. Matter decays. The cosmos grows colder and more dilute. Entropy, the tendency of systems to become more disordered, climbs relentlessly. Eventually, stars stop forming. Black holes slowly evaporate through a process called Hawking radiation, giving off faint energy as they vanish over unimaginable timescales. And after trillions upon trillions of years, a dead, cold universe. No light, no motion, no structure, just a sparse, frigid sea of particles, spread too thin to do much of anything. Heat death sounds cozy at first, but it's really a euphemism for nothing happening, forever. Even quantum fluctuations, which once birthed particles from nothingness, will go quiet. No more sparks. No more surprises. It's not a fiery apocalypse. It's a slow fade. A cosmic lullaby with no final note. Option 2. The Big Crunch. This one's more dramatic. If the universe contains just enough matter, or if dark energy changes in just the right way, gravity could eventually halt expansion. Then reverse it. Galaxies would begin moving toward each other. The cosmic web would collapse. Clusters would merge. Temperatures would rise. And everything, every atom, every quark, every photon, would fall inward until all matter and energy crushed into a dense singularity. A reverse Big Bang. A fireball in rewind. Space-time unraveling into itself. Historians still argue whether this would be a true end or the start of a new cycle. A new Big Bang, perhaps. A cosmic bounce, repeating forever. But current data suggests this isn't our fate. The universe appears to be expanding too quickly. Dark energy is winning. Which brings us to the third, and arguably scariest, option, the Big Rip. Remember how we said galaxies are moving away faster over time? That's due to accelerated expansion, driven by dark energy. Now imagine if that acceleration keeps increasing, faster and faster, until not even atoms can hold together. In this scenario, dark energy doesn't stay constant. It strengthens. First, galaxies drift apart. Then, individual galaxies are torn apart. Then stars, then planets, then molecules, then the fabric of spacetime itself. Eventually, expansion overwhelms even the atomic bonds. Electrons fling away from nuclei. Particles shred. Time itself rips apart. How dramatic this sounds depends on the properties of dark energy, specifically a parameter called the equation of state, often written as W. If W drops below -1, a big rip is mathematically on the table. Don't panic. Even if that were true, the rip wouldn't happen for another 20 to 30 billion years. So, plenty of time to finish your degree. Still, it raises the unnerving possibility that expansion could turn hostile. That the same process which gave us galaxies and stars might eventually destroy them. A gentle stretch, becoming a tear. Quirky fact. Some cosmologists once jokingly named this phantom energy, like something haunting the universe, pulling at its seams with ghostly fingers. But there are other, even stranger endings being whispered in physics departments late at night. Like vacuum decay. What if our universe isn't in its lowest possible energy state? What if it's in a false vacuum, a kind of cosmic pothole, and someday, a quantum fluctuation knocks it into a deeper, true vacuum? This would trigger a vacuum bubble, expanding at the speed of light, rewriting the laws of physics as it goes. You wouldn't see it coming. One moment you're folding laundry. The next, atoms no longer exist. Boom. Gone. Scientists say this is possible but extremely unlikely, which is sort of like hearing that Earth could be hit by a rogue neutron star. Comforting. Sort of. Another possibility? We don't know the ending because we're not in a closed story. The universe may be part of a multiverse, or a simulation, or something entirely beyond our comprehension. The end might not come in our timeline at all. Which brings us to the ultimate shrug of cosmology. We don't know. Not just about the end, but about the rules themselves. We model them, test them, refine them. But at the outer limits of knowledge, things get hazy. Time, space, entropy, expansion, these aren't simple gears. They're fluid, woven from math and mystery. Maybe the universe ends in silence. Maybe it ends with a bang. Maybe it just loops. Maybe you're living in the echo of 100 previous endings already, each one leaving behind a slightly different set of rules. You roll onto your back and stare into the ceiling, imagining the final seconds of the cosmos. Not with fear, but with awe. The idea that everything you've ever known is temporary, and yet, worth knowing anyway. The universe might fade, but the story of it, what you've discovered, wondered, felt, that lingers. You were part of this timeline. You witnessed expansion. You asked what it means. And you held the possible endings in your mind like constellations, each one glowing with a question mark. How will it end? Maybe quietly, maybe suddenly, or maybe not at all. You're still here. Against a backdrop of silence stretching toward eternity, your breath rises and falls in sync with the whisper of the expanding cosmos. And now, comfortably wrapped in the knowledge of distant heat deaths and speculative rips, you're ready to face something even more mysterious. The shape of it all. That's right. Tonight, we're tackling the geometry of the universe. Not how it looks with stars and galaxies, but the actual shape of space itself. If the universe had an edge, what would it look like? Could you walk to it? Poke your head around the corner? And if it doesn't have an edge, how can it be expanding? These are the sorts of questions that make philosophers spill their tea and physicists pull out chalk in frustration. Let's break it down. Einstein's general relativity tells us that matter and energy curve space. It also tells us that space can have three possible large-scale shapes: flat, closed, or open. Option 1, flat. This is what most current observations support. A flat universe follows the rules of good OL, Euclidean geometry. Parallel lines never meet. The angles of a triangle always add up to 180 degrees. It stretches on forever in all directions, like an infinite cosmic grid. Neat, clean, chill. Option 2, closed. This one's more like the surface of a sphere, but in 3 dimensions. Travel far enough in one direction, and, in theory, you end up where you started. There are no edges, just a looping, finite space. Kind of like a cosmic video game map with perfect wraparound. This universe is finite, but unbounded. It bends inward. Option 3, open. Now we get weird. Imagine a saddle shape, a hyperbolic curve. In this universe, triangles add up to less than 180 degrees, and parallel lines eventually diverge. It's infinite and expands forever, but space itself is negatively curved. So which one do we live in? According to data from the cosmic microwave background, especially from satellites like WMAP and Planck, space is very close to flat, with a margin of error so tiny it could fit inside a neutron's tear. But here's the quirky part. Flatness doesn't mean simplicity. Even a flat universe can have complex topology. It might wrap around in strange ways, like a 3D torus. Imagine playing Minecraft on a donut-shaped world. You walk in one direction, and boom, you're back where you started, without ever hitting a wall. Historians still argue whether the universe loops around itself, hides its true topology behind the horizon, or simply goes on forever like an endless sheet of cosmic paper. Some scientists have searched for repeating patterns in the sky, like identical galaxy clusters showing up in opposite directions, clues that space loops. So far, nothing conclusive. But absence of evidence isn't evidence of absence. And here's a mind-bending thought. The visible universe might be just a tiny speck of a much grander structure. A curve we can't detect because we're too small to see it. It's like standing on a massive globe and declaring it flat, because your legs are too short to detect the curve. So when we say flat, we really mean locally flat. Like, as far as we can tell with the tools we have right now. And why does this shape even matter? Because the geometry of space determines how light travels. It shapes the formation of galaxies. It influences the fate of the universe. A flat universe with dark energy expands forever. A closed one might crunch back down. An open one spirals into cold emptiness faster than your Monday morning optimism. It also matters because it tells us about the initial conditions of the Big Bang. To get a universe this flat, with this much uniformity, some kind of early inflation had to do a very precise job. Like 10 trillion decimal points kind of precise. The fact that we exist in such a flat, balanced cosmos is either a sign of deep underlying physics or one cosmic coincidence. Which brings us, softly, gently, into the realm of the anthropic principle. This idea says, maybe the universe looks the way it does, because we're here to observe it. Not that it was made for us, but that only universes with these conditions can support conscious observers. So of course we find ourselves in one where the math just barely balances. It's like waking up in a hotel with breathable air, drinkable water, and free Wi-Fi, and realizing, oh, maybe this hotel just happens to be one of the rare ones where someone like me could actually check in. Is that satisfying? Not really. But it's one way to explain the almost absurd precision of our universe's initial state. You lie there, thinking of geometry in a new way, not as the painful class you slept through in 9th grade, but as a living shape around you. A space that stretches, loops, or curves beneath your bed, around your room, through the sky. Invisible. Immense. And as you picture yourself on this sphere-saddled donut infinity plane of existence, a final thought tiptoes in. What if the shape isn't static? What if, over billions of years, the shape of space changes? Not because of movement, but because of expansion itself. Dark energy, density shifts, quantum fluctuations. What if they warp the shape in real time? Like ripples on an inflating balloon? Some models suggest the curvature of space might have evolved, especially during inflation. Maybe it started closed or open and flattened out. Or maybe it's still shifting right under our feet. But we wouldn't notice. Not in one lifetime. Not even in 100. Space hides its shape well. And we're just learning how to feel its curves. So here you are, lying on an invisible trampoline, stretched by galaxies, shaped by energy, gently curling in directions your senses can't follow. And the best part? You're allowed to wonder about it. That's the miracle, really. Not that space has a shape, but that you're in it, with a mind agile enough to ask the question. What shape is the universe? Tonight, it feels a little bit like a cradle. The shape of space still echoing in your thoughts. You now drift toward another puzzle that gently tickles your mind, one that combines wonder and terror in equal parts. You've asked about expansion. You've dreamed of endings. Now, you're ready for the question that lies at the heart of all time-bound thought. Did the universe have a beginning or not? Sure, we call it the Big Bang, but let's be real. Most people imagine it wrong. You probably picture a fireball exploding into darkness, stars blasting outward like cosmic fireworks. But remember, the Big Bang wasn't an explosion in space. It was an expansion of space. There was no before, no dark void waiting to be filled. There was no time, no place, no ticking clock. All of that, the hours, the inches, the ideas of before and after, was born in that moment. It's hard to swallow, right? A moment with no moment before it. Historians still argue whether time began at the Big Bang or whether it simply emerged, unfolding like a story you're already halfway through but didn't notice until now. But here's a twist. We don't actually know what happened at t=0. We can trace the universe back to a trillionth of a second after the Big Bang. We can model the temperature, the density, the particles, even the sound waves humming through the plasma. But at the actual starting point, the physics breaks down. Our equations implode. General relativity and quantum mechanics, those two pillars of modern science, go to war. Singularities show up. Infinities appear. The math throws up its hands and says, nope. This is where quantum gravity steps in. We need a theory that unifies the very large, gravity, space, time, and the very small, particles, quantum fields. And right now, that theory doesn't exist. Some candidates include string theory, where particles are tiny vibrating strings, and loop quantum gravity, which proposes that space itself is quantized, made up of discrete loops, like the pixels of spacetime. In these frameworks, the Big Bang might not be a beginning at all, but a bounce. Yes, some cosmologists believe our universe could be the rebound from a previous collapsing universe. The Big Bounce. Before the bang, there was a crunch. An entire universe, collapsing into a tiny point, then re-expanding into ours. No edges. No start. Just an endless rhythm of bang, expand, contract, bang again. Other models offer even stranger origins, like eternal inflation, where new universes constantly bud off from a vast inflationary field, each one with its own physical constants, its own rules, dimensions, and timelines. In that view, the Big Bang was just one pocket of a grander multiverse. Ours happened to inflate into something stable. Others? Who knows? Maybe they blink out in microseconds, or expand into universes where gravity is too weak for stars to form, or where time flows sideways. And yes, this means we could be just one bubble among countless others, an infinite foamy sea of universes forever bubbling and bursting. You curl into your pillow a little more tightly. Because if there's no true beginning, what about meaning? What about origin stories? That's where the philosophy creeps in. The urge to define a why behind the how. But the universe doesn't answer to our expectations. It just is. And whether it had a beginning, or is part of an eternal cycle, or is one branch of an infinite fractal tree, it's still unfolding right now, all around you. And you're not just observing it. You're part of that unfolding. Think of this. The atoms in your body were forged in stars. The carbon in your cells was built during fusion. The iron in your blood was born in supernovae. And those stars formed from clouds of gas seeded by the early universe, which itself emerged from quantum fluctuations in a sea of raw possibility. You are the outcome of a process that stretches backward not just in time, but in transformation. From nothingness, to energy, to matter, to life. Fringe fact? Some cosmologists toy with the idea that the universe creates observers in order to observe itself, that consciousness is not incidental, but essential, that the cosmos wants to be known. A bit poetic? Yes. But late at night, when the science settles and the questions swirl, it doesn't sound so crazy. Because whether the Big Bang was a beginning or a bounce, whether it was one of many or the only ever, you exist within its story. The space-time fabric cradles you, expanding, flowing, whispering. And if there was a beginning, it wasn't in a place. It was everywhere. Every particle, every photon, every speck of matter you've ever seen once shared the same point. You, the moon, your favorite mug, they were all once compressed into the same primordial soup. You are not separate from the universe's beginning. You are its continuation. So tonight, as the dark wraps around your limbs and the ceiling dissolves into stars, let your thoughts drift not toward where it all started, but how it keeps becoming. No beginning, or maybe a beginning every moment. Your thoughts, now softened like moonlight on still water, swirl gently around the idea that the universe might not have had a beginning, or might have had one so strange that it's barely comprehensible. And just as you begin to settle into that paradox, we tiptoe into a new and equally mesmerizing question. What lies beyond the observable universe? You know, the part we can see, the so-called observable universe, is only a small slice of the whole. It stretches about 46.5 billion light-years in every direction from Earth, forming a sphere that contains every photon that's had time to reach us since the Big Bang. But what about beyond that? Outside that sphere? What's out there? Here's the short answer. We don't know. But we're very curious. And curious minds do not go gently into ignorance. Let's start simple. The observable universe isn't the same as the whole universe. It's just the part whose light has reached us. It's like standing on a mountaintop at night with a lantern. You can only see as far as the glow allows, but the world continues beyond the dark. And if the universe is infinite, as many models suggest, then that means beyond the edge of our cosmic horizon are more galaxies, more stars, more dust, more planets. Possibly infinite copies. Possibly endless variations. Somewhere out there could be another you. Exact same DNA, same thoughts, same dreams. Except maybe you brushed your teeth with your left hand tonight instead of your right. It sounds like sci-fi. But mathematically, in an infinite space, all possible configurations of matter not only can exist, they must exist. Repeated, over and over, like patterns in an eternal quilt. Historians still argue whether the observable limit should be seen as a meaningful boundary or just a practical one. After all, it's not a wall. It's a horizon, a limit set by time, not by space. Every year, light from farther away reaches us. The sphere grows. But even with perfect instruments, we'll never see it all, because the expansion of the universe is outrunning the speed of light. There are galaxies so far away that their light will never reach us. Not because they're hidden, but because space is growing faster than light can travel through it. They're gone to us, forever unreachable. And here's where things get truly surreal. What if the regions beyond our horizon don't just contain more of the same, but entirely different physics? Some theories, especially those born from eternal inflation, suggest that what we call the universe is just one bubble in a vast multiverse. Each bubble sprouts from the inflationary field, expanding into its own cosmos with its own constants, its own particles, maybe even its own dimensions. In our universe, gravity behaves a certain way. Electrons have a specific charge. Stars burn with a particular nuclear fusion rate. But in a neighboring universe, those values might be totally different. Some might collapse instantly. Others might never form atoms. A few could spawn intelligent life made of liquid crystal that communicates in harmonics and eats gravity for breakfast. We can't observe these other universes directly, but the math, the models, the whispers in the data, they all hint at possibilities beyond our reach. One fringe idea? If two bubble universes collide, they could leave a bruise, a circular imprint in the cosmic microwave background, like ripples from a bump on spacetime. Cosmologists have searched the sky for these signs. So far, nothing confirmed. But the idea alone is enough to widen your eyes in the dark. Another strange possibility? That our own bubble might one day collide with another. What would that feel like? Spoiler, nothing good. If a faster expanding universe smacks into ours, its laws override ours. Like hitting reset on the game of existence. Molecules disintegrate. Light stops behaving. Time-space gone. But again, extremely unlikely. Like, worry about this after heat death unlikely. Still, it shows how small our perspective is. We live inside a bubble, inside a sphere, inside an idea we don't fully understand. And you, curled beneath your blanket, are at the very center of your own cosmic horizon. Wherever you go, the observable universe centers around you. Not in a special way, just geometrically. The same is true for any other observer. Every being, anywhere in space, has its own observable sphere, its own limit of light, its own center of vision. Which means that space is not just vast, it's also relational. What's beyond your universe is right here for someone else. And if the universe is infinite, then there are an infinite number of observable universes nested inside a greater whole. Each one unique. Each one limited. Each one, a flicker of curiosity trapped in a bubble of time. You're floating through one of them now. So what lies beyond? Maybe more stars. Maybe more universes. Maybe the raw field of inflation itself, endlessly birthing bubbles. Or maybe nothing. A kind of beyond, where space and time break down completely. You may never know, but it's okay not to know. Because not knowing is where wonder lives. Right there, just beyond the edge of light. The idea that you're surrounded by an unseen infinity might be a little unsettling, like living in a house with no walls, only fog. But here's a softer thought to take with you. Everything you do know, every glimpse you've had of stars, galaxies, and cosmic origins, has come from a single, astonishing tool. Tonight, we shine a gentle spotlight on how we actually know any of this. Because let's be honest, space is huge. The speed of light is a cosmic speed limit, and no one's packing a ladder tall enough to touch a galaxy. So how have we figured anything out? We begin, as always, with light. Light is our most faithful messenger. Photons from distant galaxies travel billions of years to reach our eyes, carrying information about the past. In fact, every time you look up at the night sky, you're not seeing stars as they are, you're seeing them as they were. You're gazing into a time machine. The star Vega? You see it as it was 25 years ago. The Andromeda Galaxy? That's a 2.5 million year old selfie. The most ancient light we can detect, the cosmic microwave background, is 13.8 billion years old. And how do we make sense of all this incoming starlight? Interspectroscopy. It's like cosmic forensics. Every atom and molecule emits and absorbs light at specific wavelengths. When we pass starlight through a prism or a diffraction grating, we split it into its component colors, a spectrum. And in that rainbow are tiny dark lines, called absorption lines, like barcodes. Each element has its own barcode. Hydrogen, helium, carbon, iron, they all leave their fingerprints. By analyzing the pattern of these lines, we know what stars are made of. We know the temperature, motion, and composition of things we've never touched. And here comes the magic. When those lines are redshifted, stretched to longer wavelengths, we know that the object is moving away. That's how Edwin Hubble realized the universe is expanding. By comparing the redshifts of galaxies to their distances, he saw the pattern. The farther away a galaxy is, the faster it's receding. That's our cosmic ruler. But how do we measure distance in the first place? We use a cosmic ladder. No, really, that's what it's called. The cosmic distance ladder is a series of interlocking methods. Parallax. For nearby stars, we measure how their position shifts against background stars as Earth orbits the Sun. Like holding up your thumb and blinking each eye, your thumb moves. Cepheid variables. These are pulsating stars whose brightness correlates with their pulsation period. Measure the period, and you know the true brightness. Compare it to how bright they appear, and you get distance. Type I supernovae. These exploding stars always reach about the same peak brightness. Like cosmic light bulbs, we find them in distant galaxies and calculate how far their light has traveled. Each rung of the ladder builds on the one before, extending our reach from nearby stars to the far edges of the observable universe. We also use telescopes, of course, giant metal eyes that gather light. The Hubble Space Telescope gave us the deepest image of the cosmos ever taken, the Hubble Ultra Deep Field. A patch of sky no bigger than a grain of sand held over your head, filled with thousands of galaxies, each a city of billions of stars, some as they were when the universe was only a few 100 million years old. And then there's gravitational lensing. Gravity bends light. So when a massive object, like a galaxy cluster, sits between us and something farther away, it warps the light from that distant object, magnifying and distorting it. Like a natural telescope. This is how we've detected galaxies we would otherwise never see. It's also how we map dark matter. Because while we can't see dark matter directly, we can see how it warps space. Fringe fact? There's a galaxy cluster named MAX J1149 plus 2223, where gravitational lensing has let us watch a single supernova explode multiple times. Because the light is taking different paths around the cluster, some shorter, some longer, we see the event occur again and again. We're also now listening to space. Not with ears, but with gravitational wave detectors like LIGO and Virgo. These instruments sense tiny ripples in space-time caused by collisions, like black holes merging. It's like hearing the universe ring like a bell. And as technology improves, we're beginning to detect the cosmos in even stranger ways. Neutrinos, cosmic rays, radio bursts from galaxies billions of light years away. Each method fills in part of the picture. And together, they give us a layered, moving, technicolor map of a universe we've never touched. Historians still argue whether this explosion of knowledge is the beginning of a new golden age, or just a lucky moment in a longer climb. Either way, we're learning faster than ever. And here's a quiet thought. All of this, every measurement, every theory, every grand model, comes from one tiny rock orbiting one ordinary star in a forgotten arm of one spiral galaxy. You're part of a species that built tools to catch the light from the beginning of time. Tools that look back 13 billion years and say, there it is. We see you. So when you lie there in the dark, feeling impossibly small, Remember, you are part of a mind big enough to stretch across galaxies. You read light. You hear gravity. You know how stars die and what atoms dance in distant suns. You don't need to leave Earth to touch the stars. You just need curiosity and maybe a good telescope. The room is quiet now. So quiet that the only thing moving is the glow of the cosmos in your mind. Those ancient photons, redshifted and humming softly across the black. And yet, in the vastness of all you've imagined, there's one more unsettling but irresistible layer of mystery. What if the laws of physics themselves are temporary? Think about it. We've assumed, all this time, that the rules of reality, the speed of light, the charge of an electron, the strength of gravity, are constant, immutable, carved into the bones of the universe. But what if they're not? This is where cosmology starts to flirt with philosophy and physics peers over the edge of its own limitations. Let's start with something familiar: constants. We call them constants because we've measured them, and they don't seem to change. The gravitational constant, g. Planck's constant, h. The fine structure constant, alpha, which controls how light and matter interact. Alpha is especially fun. It's dimensionless, a pure number, around 1/137, and it determines the strength of electromagnetic interactions. Without it, atoms don't exist. Light doesn't behave. Chemistry vanishes. Now, here's where things get spicy. A few measurements, distant quasars, absorption lines in ancient clouds, have hinted that alpha may have changed slightly over billions of years. Just a smidge, like 0.00001%. But even that tiny drift would be cosmic dynamite. Because if physical constants change, then the laws of physics themselves are evolving. And if they can change, where do they come from in the first place? Some theories suggest that these laws emerge as the universe cools, like phases of matter. At high energies, close to the Big Bang, the forces of nature might be unified. As the cosmos expands and cools, they split. Gravity over here, electromagnetism over there, strong and weak forces getting their own offices. In that view, the laws aren't eternal, they're contextual. Historians still argue whether the universe has always followed the same rules or whether it undergoes phase transitions, like ice melting to water. Entire epochs may have had different physics. Gravity might have been stronger. Electrons might not have existed. Light might have been sluggish or absurdly fast. There's also the idea of dimensional change. Some early universe theories propose that space may have started with more than 3 dimensions, and some of them curled up as the universe expanded. That would mean reality used to be fundamentally different. Imagine waking up to find that time had gained a second direction, or that gravity now repels instead of attracts. And here's the kicker: this might not be over. If dark energy evolves, or if hidden fields interact with known particles, the future universe could slowly shift into new physics again. The speed of light could change. The vacuum could decay. The rules might drift until matter can no longer form. You won't notice at first. The changes would be subtle. But over eons, stars would stop burning. Planets would fall apart. The familiar world would dissolve, not from violence, but from the gentle unraveling of the rules that hold it together. It's the ultimate quiet ending. Not a bang, not a whimper, just a rewriting of reality's operating system, line by line. Quirky fact: in some simulations, scientists have imagined what other universes might look like if the constants were tweaked slightly. Most of them are sterile. No atoms, no stars, just a fog of chaos. But a few are strangely viable. A universe where gravity is weaker but fusion is stronger. A universe with 2 kinds of time. A universe where light moves like sound, rippling through a thick medium. A universe without space, only probabilities. And in one version, the laws shift over time, but slowly enough for life to adapt, evolving not just biologically, but physically, to suit new realities. Fiction? Maybe. But math allows it. And that's what keeps cosmologists up at night. Because if the laws can change, then nothing is sacred. Not mass, not time, not even logic in the way we know it. You roll onto your side now, feeling the mattress curve beneath you like space-time beneath a planet. You think of constants as stars, fixed points guiding your ship. But now, you wonder if those stars might drift. And still, somehow, you're okay with it. Because whether the laws were written once or rewritten constantly, the miracle remains. They work. Right now, here in this moment, the rules are stable enough to breathe, to think, to ask. You are made of particles that follow those rules flawlessly, while your brain questions the rules themselves. That's like a poem writing about its own meter, a song wondering if notes are optional. The universe may not be permanent, but curiosity is recursive. It questions everything, even itself. And if someday the constants shift and atoms forget how to hold each other, let this thought linger like a last echo. Once upon a time, the rules aligned, and you existed. The walls of the universe may be shifting, invisible, even impermanent, but here you are, breathing through it all. And with that breath comes the next question, one that flickers quietly in the minds of both astrophysicists and philosophers. Is the universe conscious? Now, before you roll your eyes, gently, of course, we're trying to get sleepy. Understand this isn't just late-night dorm room talk. This is a genuine debate at the blurry boundary between cosmology and cognition. Let's start where things feel solid. You are conscious. That much, at least, we think we know. You experience thoughts. You dream. You ask weird questions at 2 a.m. like, what if time doesn't exist? And you're made of atoms. Those atoms are made of quarks and electrons, which obey the same physical laws as everything else in the universe. But somehow, when arranged just so, in your neurons, in your brain, they create something more, awareness. So, is consciousness just a byproduct of complexity? If you take enough matter, stir it up under the right conditions, and wait a few billion years, does consciousness just emerge? That leads to the question, if consciousness can emerge from matter, and matter is everywhere, could it arise in more than just brains? What if galaxies think, in their own slow, silent way? What if space-time itself has awareness? Welcome to panpsychism, the idea that consciousness, or at least the seeds of it, may be a fundamental feature of the universe. Not something special that happens within the cosmos, but something the cosmos is. This is not a new idea. Ancient thinkers whispered it in different forms. Some indigenous traditions speak of a world that sees. Eastern philosophies often reject the sharp division between mind and world. Historians still argue whether modern science is finally circling back to old mysticism or just colliding with the limits of its own language. But here's where it gets delightfully strange. Some physicists, not fringe bloggers, but real, tie-wearing scientists, have asked whether consciousness is linked to information. In this view, consciousness isn't some spooky ghost inside your brain. It's the ability to integrate information, to process and respond to stimuli in a meaningful way. Enter integrated information theory, IIT. It tries to mathematically describe consciousness by measuring how much a system knows about itself. Your brain? Lots of integration. A rock? Not so much. But what about black holes? They process enormous amounts of information. They affect time, space, and entropy. They may even store the entire history of everything that falls into them. Could they possess some glimmer of awareness? Some scientists propose that black holes might be the most information-dense objects in the universe, and if information is linked to consciousness. Well, you see where this is going. Another quirky twist? Quantum mechanics introduces a role for observers. The infamous wave function collapse depends, at least in some interpretations, on observation. Does that mean a mind is required to collapse reality into being? Or just a measuring device? We don't know. But we do know that consciousness and reality are tangled, like threads in the same scarf. And then there's the anthropic principle again. The idea that we observe a universe fine-tuned for life. Because if it weren't, we wouldn't be here to notice. But the principle leaves the door open to something deeper. What if consciousness isn't just noticing the universe, but necessary for its unfolding? What if reality needs awareness to actualize? That without someone to perceive time, time doesn't flow? Now breathe. Let that ripple across your pillow. There's also the simulation hypothesis, which, surprisingly, shares echoes with these ideas. If the universe is a simulation, an immense, hyper-accurate rendering, then it's built on information. And if so, consciousness might be the key that renders reality in high definition. Your act of noticing might be what brings the cosmos into sharp focus. Are we saying the universe is conscious? Not exactly. But maybe, like you, it contains consciousness. Perhaps as a rare bloom. Perhaps as something more intrinsic. You are not separate from the cosmos. You are a node within it. A brief flicker of awareness through which the universe examines itself. Carl Sagan once said, "We are a way for the cosmos to know itself." You are that way. Your dreams, your fears, your tiny human joys, they are the universe's first-person experience, happening at human speed. And as your eyes grow heavier, think of the paradox. A cold, vast universe filled with violent explosions and frozen voids that somehow gives rise to lullabies, to whispered questions, to stories told in the dark. The universe may not be conscious in the way you are, but it created a being who can wonder about it, who can look into the abyss of space and say, "I am here." And maybe that's enough. As you lie there, comfortably tangled in your blanket and cosmic riddles, you begin to wonder, not just about what the universe is, but whether it might be well. Alive. No, not in the creepy horror movie. The universe is watching you way, but in the biological, systematic, self-regulating, breathing kind of way. Could the universe itself be a living organism? A system not just structured, but alive in some fundamental sense? It's a soft idea with hard edges, part metaphor, part mindbender. Let's ease into it. Start with this. What defines life? Biologists usually say a living thing must be made of cells, grow, adapt, reproduce, respond to stimuli, and maintain homeostasis. So an amoeba? Sure. A rock? Nope. But when you zoom out, and then way out, those criteria start to get blurry. Take the universe. It grows, expands, changes, evolves, contains energy flows, complex structures, feedback loops. It responds to gravity, temperature, entropy. It even recycles matter through stars, galaxies, black holes, and back again. It doesn't have cells, but it has galaxies clustering like neurons in a vast brain. The cosmic web, that delicate lace of dark matter and light, eerily resembles the neural structure of a human brain. No joke. Studies have compared the distribution of galaxies to the structure of neurons and found surprising mathematical similarities. Two systems, separated by scale and substance, behaving in strangely parallel ways. Fringe? Maybe, but not without merit. Historians still argue whether comparing the cosmos to a living thing is poetic nonsense or an overlooked metaphor with teeth. After all, life is just a highly organized pattern of information and energy, and so is the universe. Let's dig deeper. Some cosmologists and physicists have toyed with the idea of the universe as a complex adaptive system. That means it learns, self-organizes, and adapts, not with intention, but through natural selection and feedback. Sound far-fetched? Consider the idea of cosmological natural selection proposed by physicist Lee Smolin. He suggests that black holes might be birthing new universes, each with slightly different physical constants. Universes that produce more black holes then reproduce more. Over time, this favors the creation of universes tuned for complexity, structure, maybe even life. Kind of like Darwinian evolution, but on a multiversal scale. That means our universe might be the cosmic equivalent of a fit organism, optimized for growth, reproduction, and internal complexity. Here's another angle. Some thinkers propose that the universe exhibits something called autopoiesis, the ability to create and maintain itself. This is what defines living systems, self-production. You grow your own skin cells. A jellyfish regenerates. A plant stretches toward the sun. Well, what's the universe doing? Creating stars, forming matter, evolving galaxies, birthing brains. It's not just expanding, it's sculpting complexity. From randomness to order, from simplicity to minds that can ask questions like this one. Even entropy, the increase in disorder, doesn't stop complexity. Paradoxically, it drives it. Local decreases in entropy, like you, are allowed as long as the universe as a whole keeps drifting toward chaos. That dance between order and disorder? That's biology. That's metabolism. That's life. You see, if life is just the temporary resistance to entropy, then you're a local flare in the cosmic fire. A match lit in the cold. A brief song in the static. And the universe? A symphony of such songs. There's even a name for this idea, the living universe hypothesis. It doesn't say the universe has a heartbeat or favorite color, but it suggests that the same principles that make life work on Earth, feedback, complexity, adaptation, might govern the whole system. A galaxy forms. A star dies. A planet spins into habitability. Life arises. Intelligence blooms. And maybe, just maybe, some of that intelligence begins to understand the system it's inside. That's you. Fringe fact? Some scientists speculate that advanced civilizations, billions of years ahead of us, might eventually merge with the structure of the universe itself. Not just sending ships through space, but transforming themselves into space, embedding thought and memory into quantum fields and dark matter. It's the ultimate sci-fi twist. Life doesn't just live in the universe, it becomes the universe. And if that happens often enough across time and space, then perhaps the universe isn't just alive, it's awakening. You take a slow breath. Because maybe this living cosmos doesn't have organs or instincts. Maybe it doesn't need a pulse. Maybe it lives through emergence, through laws, through the balance of expansion and gravity. And maybe, just maybe, you're a tiny part of its nervous system. A neuron firing one sleepy thought. What if the universe dreams? And tonight, that dream is you. You've entertained the idea that the universe might be alive, or at least alive-ish in its structure and cycles. But now your thoughts swirl a little deeper, a little more abstract. into a place where logic feels like it's draped in fog. Because here comes the grandest twist of all. What if reality itself isn't real? Now hang on. This isn't a you're in the Matrix kind of story. Although, to be fair, we'll touch on that. This is bigger. This is about peeling back the curtain on the stage, only to find that the stage might not even be there. Let's begin with something grounding. You experience a world. Sights, sounds, gravity tugging at your chest, memories looping in your mind like old songs. But all of that, every sensation, is filtered through your brain. You never interact with reality directly. You just get signals. Light bounces off a tree, enters your eyes, turns into electric pulses, which your brain stitches into the idea of tree. But you don't see the tree itself. You see a brain-generated image of a tree. Now take that logic further. Your experience of space? Constructed. Your sense of time? Filtered and processed. Even the idea of a self, the sense that you are a fixed observer, comes from a particular brain configuration. This brings us to a bold idea from modern philosophy and cognitive science. Reality is a user interface. Like a computer desktop, you click on a blue folder and it opens your files. But that folder isn't real. It's a visual shortcut for something much more complex. You're not manipulating voltage on a circuit board. You're just dragging and dropping pixels. And reality might be just that, a simplified interface your brain uses to survive. Donald Hoffman, a cognitive scientist, argues that evolution doesn't favor truth, it favors usefulness. If perceiving a rock as solid helps you not stub your toe, your brain encodes that. Not because the rock is truly solid, but because the illusion works. Historians still argue whether consciousness creates reality or merely interprets it. But the further we dive into quantum physics, the blurrier the boundary becomes. At the quantum level, particles behave like probability clouds. They don't have definite properties until you measure them.